Okay, all right, here we are again and again. Bear with me just a moment. I have to get my settings checked to make sure this all is good. I believe it is. Sharing screen then. And as usual, I have to clean up my desktop clutter. And here we go, looking at example 3 now. Okay, so whoops. All right, so we got another line integral to compute here. And now notice this is in 3 dimensions. For one thing, the vector field that's given has 3 coordinates, right? And then you also can see here that just from the way this is written, it's clear that there are 3 variables. Now, I emphasize, note it isn't clear from this, right? That alone, there are no z's in there. So, you know, this business about looking at the algebra and looking at which variables are there and which variables are not there, you can't really rely on that if, you know, at least in the one direction. When the z is there, you know, but when it's not, it doesn't mean anything. Okay, anyway, clearly, 3 coordinates in the vector field. This is in 3 dimensions. And so here we are. And let's clean up from last time here. So we are back in R3 doing vector calculus. We've been asked to compute a line integral. And let's start thinking about what we have. So again, we have a vector field given. Fine. The diagram tells me I should compute the curl of my vector field and see what I get. And so we do that. And here we go. Computing the curl. Let's see the first coordinate, the y partial of that, which is 0, minus the z partial of that, which is 1. Then we have the z partial of that, which is 0, minus the x partial of that, which is 1. And then we have the x partial of that, which is 0, minus the y partial of that, which is 1. So there's our curl. It's not 0. Being as we got not 0 there, that means there is no anti-gradient function. That means the fundamental thermal line integrals is off the table. It's not going to happen. Don't waste your time trying to find an anti-gradient or anything of the sort. Okay. All right. So in fact, I think what I'm going to do here is I'm going to now circle just this, because that's the only, you know, this being a circulation is my only hope for possibly being able to use one of these cool theorems. And this is right out. So I'm just going to cross that fully out. Okay. All right, next, I have a curve given to me. I need to understand this curve. In particular, what I really need to know is there an anti-boundary surface? That's what we really want to know. And now, if there were a way for me to conveniently compute the boundary points of my curve, right, then that would be a way of deciding. So with that in mind, let's look back to here. And, you know, finding the endpoints isn't particularly convenient the way this is written. The way this is written, I'm just given 2 surfaces, and I'm told that my curve is the intersection of those surfaces. It's not given parameterized, so I'm not going to really need to capitalize on that, you know, boundary lifetime theorem business. It doesn't help me. So I'm going to just draw a picture of these surfaces, try to understand what my curve is. So here we are in 3 dimensions, and let's draw this one first. There's a cylinder. That looks like the hard one, so I like to do the hard one first. It's a cylinder. It's centered on the z-axis. Radius is 1. So not that it's particularly hard, but nevertheless, it's harder than this one. This one's just a plane, and the plane kind of cuts through here, you know, kind of somehow. Something like that. The intersection then of these 2 things, my curve being that intersection, is going to be something kind of like that. There we go. Okay. All right. Is this a boundary? Yeah. I mean, again, it kind of jumps out of the picture at me in this case. I can just see right away. Yeah, sure. This is easiest example. This is the boundary of that piece of the plane. Okay, so back to the diagram, and I didn't even need to do that at all, but yes, there is an anti-boundary surface. That means that yes, I can use Stokes's theorem, and we can proceed. So in order to use it, of course, now I know what my surface is. We're good on the surface. I am going to need to take the vector field that I was given, the vector field whose line integral I want to compute. And I'm going to need to find the curl vector field, because that curl, that curl is going to be the integrand for my flux integral. Oh, good news. We already computed that curl. Right, here it is, the curl right there. So this curl calculation did us a couple of favors. Computing this curl, on the one hand, that's what eliminated the fundamental theorem of line integrals as a possibility. It's also, as we see now, going to be my integrand for my Stokes' theorem calculation. Okay. All right. So I need to compute then, let's see here. So I'm going to call this surface S. I need to compute the flux through S of the curl dot ds, and so you can plug and chug. And again, I'm going to leave the details to y'all to work that out, if you're so inclined, of course. There are a couple little issues that I have ignored here, though, that we do need to talk about. Notice I didn't do anything with the orientation, and that is a problem. Orientations matter. Orientations are a big deal. So let's think that through now. We are given, in terms of orientations, that my initial curve is oriented counterclockwise as seen from above. Now, of course, you've got to say as seen from where when you're talking about clockwise and counterclockwise in 3 dimensions, because from the other side it always looks the opposite. So as seen from above, counterclockwise. Okay, so that means like this. Okay. All right, now what does that mean then about the orientation of my surface here? Well, my surface has to be oriented in such a way as to induce the correct orientation on the curve, this given orientation on the curve. So I got to think through both options. Now, again, I'm going to start with the wrong one so that we can see both in action. And so let's consider the possibility that maybe the orientation is downward like that. Well, so right hand, thumb in the direction of that normal vector. Look at what your fingers do, right? And well, that would have me going around that way, and that's just wrong. That's not the correct orientation. So of course, then I try the other. Try the upward orientation, and again, right hand, thumb in the direction of the proposed orientation normal. Look at the fingers. How does that make a swirl? And the swirl is the correct direction. And so there you go. That's the correct orientation on my new surface that I've made up. So this here is oriented upward. Okay. All right. So how do we compute this flux? Now, there's a couple of things to say about that. The direct way to do it would be to kind of forget about we don't need, well, I guess it's harmless. I'll leave it there. But we don't really need these surfaces immediately. We're not really doing anything with these surfaces other than how they help us understand the yellow surface. the new surface S. So parameterize and plug and chug, right? And what I know about S is, let's see here, well, S is part of my blue surface. Let me do it like this. It's part of that blue surface. I can solve for Z. Therefore, viewing it as a graph, I can therefore use the graph parameterization. So S, T, negative S minus T. My graph parameterization, take the various partials, blah, 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 check and make sure that it's oriented correctly. Make sure that it is indeed oriented upward. If it's not, you have to put in your little apology. Whoops, I accidentally parameterized this backwards, and then put in the corresponding minus sign, and then just proceed. Keep going. That minus sign fixes the issue, but you do have to check. You got to make sure to check and make sure that it's right. In this case, it's going to be right. Okay. All right, here's another thing that some students would do in this case, trying to take advantage of clever. And it's a noble effort, and I support clever, right? But only when it actually works. So a lot of students would look at this and say, oh, okay, parameterizing, and then there's partials, and then there's a cross product, and then there's oh my gosh, there's so much there. Hey, check it out. I can bypass all of this by just noticing that my normal vector, right, that normal vector, I mean, I can look at the equation of the plane. From the equation of the plane here, doesn't it immediately follow that n equals, and I want to keep this a question mark, 1, 1, 1. Right? Isn't that nice? So it seems. You can probably tell from my tone of voice that this is this is not right. Danger, right? But it's tempting, right? You see the allure of oh, it's the equation of a plane. I know the normal vector. Okay. No, you cannot do this. When you're using this capital N thing here, right? When you're going to rewrite your flux integral as an integral of curl dot capital N ds dt, when you're going to do that, the point is this has to be the parameterized normal vector. This has to come from the parameterization through which you are pulling back, because its magnitude is the stretching factor. And without knowing that stretching factor, you can't do the pullback. So you have to know it's not good enough to just have any old normal vector. You have to have the unique capital N normal vector that comes from the parameterization. And that's not what happened here, right? This did not come from any parameterization. And really then, I shouldn't call it in the first place. This capital N, the N that's going to be used in doing actual parameterization pullbacks, should only come from the parameterization, because it has to. Otherwise, your stretching factor is all wrong. Okay, so heads up about that. Now, here's another little coincidence. It turns out that if you were to do the wrong thing here, if you were to, let me get rid of my, oh gosh, where's that? Here we go. If you were to just write down this, which I emphasize is wrong, but if you were to just write that down, numerically it's correct. And that will happen surprisingly often, but that does not make this okay. The reasoning, again, I cannot emphasize this enough. You've heard me say it a million times. And the only reason I won't say you'll hear me say it a million more is because the semester is approaching the close. But this course And the exams and the grading of the exams is not about the answers, it's about the reasoning, right? And so this reasoning is just as wrong as reasoning, getting numerically the correct answer as it is getting numerically the incorrect answer. The reasoning is equally bad. Anyway, don't step on that landmine. It's a dangerous landmine to make an inappropriate, an invalid argument, seemingly easy. And again, you see daylight at the end of the tunnel. And you're like, oh my God, look how easy I can find myself a normal vector. If you do that, you cannot use that as the parameterized normal, which is what we're going to do with it here. Okay. All right, now let me show you another tempting approach, and this one's not wrong, it's just not useful. So the next tempting thing to try to do would be to say, okay, well, look, I can't call this my parameterized normal vector, but I'm going to call it m because I want to reserve little n for being the unit normal. And this I can still say is 1, 1, 1. That's totally fine. That is normal to the plane after all. That's fine. And then I can make that a unit vector by dividing by the square root of 3. Now we've got a unit normal vector. And then I can say, and this is totally fine, that I've got curl dot little n ds. This is perfectly legal. No problem. And having computed our curl already, let's see here. Yeah, computed the curl already there. Yeah, sure. Here's the problem there. The problem here is that it remains. I'm going to need to know what this ds differential is on the end. And how do I compute the ds area differential? Well, by parameterizing, right? So the whole point, in some sense, of trying to write down your unit normal, the whole point of that was to avoid parameterizing in the first place, parameterizing and having to find capital N. I'm trying to avoid that. Well, in this case, in our attempt to avoid it, well, we didn't avoid it. We still need to parameterize and find that capital N so we can find our ds. So this approach doesn't really buy you anything. Arguably, all it does is expose you to the possibility of arithmetic errors or other forms of little oopses. So this isn't wrong, but I wouldn't advise it. I don't think it's a good choice. Okay. All right. Now, in this case, it's not a good choice. Now, if it had turned out, imagine, for example, that my surface was more recognizable. Right here, I've got my surface is it's an ellipse of some sort, but I don't know the semi-major axis, semi-minor axis. I don't know what those are, and so I can't just write down what the area is, right? But if it were a disk, or if it were a some other easy known shape whose area that I know, then I don't have to compute the parameterized differential at all. I can just write down the area, multiply the integrand times the area, because the integrand's a constant. When you have a constant integrand, factors right out, multiply by the area. Those cases are great. And so those are the cases where we're sure this is a really good idea to do it this way. Okay. So there's a lot going on with this example. It's a lot to say about the different possible approaches that you could take and that you can't take. And there we go. Okay, so let's move on to the next one. This next one looks pretty similar. It's, in fact, the exact same vector field. And we are, again, looking at a plane intersecting the exact same cylinder, right? And again, we're computing a line integral. Okay, so a lot of this that we're about to do comes along for free. Let me, again, let's start over with the reasoning, though. So we're looking at line integrals. The vector field, we need to compute the curl. We already did. And then I'm going to need to ask if there's an anti-boundary surface. By the way, it turned out the curl was not 0, so there is no anti-gradient. So forget about this. And that's why I redrew and said, okay, what we really need to do is compute that, which, well, I shouldn't say that, which I hope I can call a circulation. I hope it's a closed curve. And then we look back and think, yeah, it is a closed curve. Yeah, sure. So we are computing a circulation. In fact, I'll go ahead and circle this whole thing. So again, we're going to be thinking in terms of using Stokes' theorem. And it's tempting to say, well, it's just a different plane, so there's going to be different details than last time, but shouldn't we do pretty much the same thing? And you could, but something really, really nice happens here. There's a wonderful little bit of good fortune. And that's what I want to write down. Okay, so we've got a line integral around a curve that is a boundary of a surface of f dot dx. And we're going to invoke Stokes' theorem and say, well, therefore, that's the flux through that surface of the curl dot ds vector. And sure, you could take this, parameterize, replace the ds vector with capital N ds dt. That would be the sort of the right down the pipe standard way to do it. Here's the bit of good news. Let's instead think geometrically this time and call this little n ds scalar. And the reason relates to what the curl is. The curl, again, we've already computed in the last problem, is -1, -1, -1. And real quick, I need to draw a picture now of my thing here. I've got, as before, oh, let's see here. I should mix my colors. I've got this cylinder intersecting with, with this plane. Oh, let's see, x minus z is 0. Okay, so that's going to be a little bit hard to draw accurately, but anyway, so the intersection here, that intersection is a ellipse, something like that. Point being, when I get my new surface, this new surface, and I want to understand its normal vector, right? I want to understand, let's think in terms of its unit, color choices, I'll use red. Its unit normal vector. It is, of course, the unit normal vector for the plane that I was given in the first place, which I can see right there. And I can immediately write down 1, 0, -1. Okay, there's the issue with the orientation, so I'm not sure. I'm going to put a plus minus out here just because I don't know yet. And yeah, I have to normalize it, so I have to divide by the square root of 2. But it's going to look something like that. And so notice then, when I do this dot product, when I dot the curl with my normal vector, dot product 0, independent of the plus or minus, right? And so whether the orientation is this way or that way, in this case, doesn't matter. The answer is just 0. So, you know, look, this is something to try to anticipate, right? I mean, there's a lot I had to write down to get to this happy conclusion, but you can kind of sort of see these things coming as soon as you write that down. you can think, okay, I'm going to need to know that normal vector, my normal vector. Well, there's a lot to say about the normal vector, but you do know it's parallel to what you can immediately observe there. And then just kind of look and see if the numbers work out, if it's, 0 or not 0. Because if it's 0, nothing else matters. And that's sweet. Okay. All right, so that's the end of this example. It does occur to me one last thing. I am going to go back to example 3 here and say one last thing about it. There's a big mess on the page here. But let me do this and write down that what we agreed on this question was that the best way to answer this question would be to compute the line integral by way of a flux integral of curl dot capital N ds dt. Namely, you'd parameterize and pull back through the parameterization. Okay, so this is the best approach that we discussed, and it might even be the best way to solve the problem. But I forgot to mention previously, and I think this is worth mentioning. There is a third option, third, fourth, fifth. Anyway, there is yet another option, and very often it's not the best. But you could just take the original question, forget about all the fancy theorems, and just parameterize the curve. View this as forget about all boundary theorems and accumulations and all the fancy stuff. Just parameterize the curve. You're given a curve, parameterize it. The vector field's not bad. It would not be a bad approach at all. So in particular, let's talk about how to do those details. And because this is getting out of hand as a mess, I am going to go ahead and just delete all this stuff. It's already been recorded. You can go back and find that stuff in the recording where we were talking about that question. Our picture something like this. Let's see. So we're on the cylinder and we're cutting it with this plane. Yeah, so that's right. So our curve is, well, I better draw, okay, the cylinder. And then the plane, hard to, like that. And so our intersection curve, something like that. And this isn't hard to parameterize. As it turns out, I can write down pretty easily my parameterization, namely X, Y, Z, using the following tricks. The X and Y coordinates come straight out of that cylinder. X squared plus Y squared is 1, which is an old friend, right? So I can parameterize X and Y coordinates by just saying cosine T, sine T. The Z coordinate, I can notice right there, in order to make sure that I stay on the plane, which of course I must, Z is apparently going to have to be negative X minus Y. And so I can just say minus cosine T minus sine T. And there you go. Whoops. That is a parameterization then of my curve. I haven't thought about the orientations, but the point is, actually, I think that is correct, orientation-wise, but not that hard to parameterize. And that means that when you plug in, and keep in mind, when you this is my X. Here, let me. Oh, missed again. Let me try that one more time. That X there in the vector field is just cosine T. It's not bad. And the Y is sine T, and okay, Z is, maybe not my favorite little bit of algebra that I've ever seen, but it's not that bad, right? So you have a kind of not that bad vector field, and we've got a parameterization. You can take the derivative and you're going to get a couple of trig integrals. So maybe this approach might be just as good as using Stokes' theorem. So, don't feel like you're obligated to use fancy theorems just because they exist, right? You're welcome to look for the reasonable opportunities when they turn out reasonably to do them like this. Because it works out reasonably. And just for comparison, though, let's point out if you were to just plug and chug on this one, not reasonable. This is going to be brutal, right? This is not tractable, and that is not a reasonable approach for a question like this one. But it's just fine here. Okay. All right. So that's examples 3 and 4. I'm going to stop the recording. Again, we'll do examples 5 and 6 in the next recording. Okay. See you in a second.